Yeah, welcome to Easy Mathematics and a new video. Today we want to discuss a nice identity involving a complex sine function, and this is the absolute value of sine of x plus iy is the same absolute value of sine x plus sine of iy. And this is pretty cool because it seems like we can distribute the sign. So it seems like distributing the sign. And this is a nice identity. So my plan for this video is, so first we prove this and then we discuss similar statements maybe for the hyperbolic sign, and the last one is if there are any other functions satisfying these properties, or what about the cosine, for example. And before we start, I want to recall a couple of facts. So the trigonometric Pythagorean theorem, then the hyperbolic Pythagorean theorem, then converting complex trigonometric and hyperbolic functions. For example, sine of ix is I times hyperbolic sine of x, and similar stuff for the cosine and hyperbolic cosine. Okay? And we proved the statement, and to get rid of the square root all the time, we consider the square of the absolute value. So let's start. So we consider the square of that, and first, so to calculate the magnitude of a complex number, it makes sense to split the complex number up into the real part and the imaginary part, and therefore we use the addition formula for the sine, and therefore we get sine x times cosine iy plus cosine x times sine iy. Alright, so this is the addition formula for the cosine. Now we use these properties. So we see cosine iy is hyperbolic cosine of x. So here we have sine x times cosine, hyperbolic cosine of y. Then here we have plus cosine x. Sine of iy is I times hyperbolic sine, so I put the I here, and then hyperbolic sine squared of y. Okay? Now we have a real part here and the imaginary part there. Okay? How to calculate the magnitude of a complex number? It's also the Pythagorean theorem. So real part squared plus imaginary part squared and then the square root, but because of the square we do not need the square root. So we have sine squared of x times cosine, a hyperbolic cosine squared of y, plus cosine squared x times hyperbolic sine squared y. Alright? Next, I want to get rid of the cosines. Therefore we use the trigonometric, so the Pythagorean theorems. So for the hyperbolic cosine, we see it's 1 plus sine squared. So we get here 1 plus hyperbolic sine squared of y plus the trigonometric Pythagorean theorem. So we put the sine to the other side, we get 1 minus sine squared of x times hyperbolic sine of y squared. Alright? Now we see we have here sine squared of x. Sine squared times hyperbolic sine squared minus sine squared hyperbolic sine squared. This cancels out, so please look carefully. And we are left with plus 1 times hyperbolic sine. So hyperbolic sine squared of y. Good. But now we can use the definition of the magnitude of a complex number. So if this is the real part and this is the imaginary part, we get this is the magnitude of sine x plus I times hyperbolic sine of y squared. Alright? So this is this step in the other direction. Now we can use here our tools. Hyperbolic sine of x is, let's see, yeah, I times hyperbolic sine is sine of ix, okay? So we get sine of x plus sine of iy, and this is exactly what we wanted to prove here. So this is done. Alright? So in the next step, for the next case, so we can think about something similar for the hyperbolic sine. And yeah, you can play around with that and you will see that this works also with the hyperbolic sine. So we get the magnitude of hyperbolic sine of x plus iy is like the same idea, like distributing the hyperbolic sine here. Okay, so this holds also. And yeah, the next one would be the cosine, and hyperbolic cosine, of course we can find some identities, but not in the sense like here, like this seems like we can distribute the sine and hyperbolic sine here. With the cosine you will find out it's not the case, and in fact there are three functions satisfying following property. So if f of z is regular and satisfying f of x plus iy, the magnitude equals the magnitude of f of x plus f of iy, plus f of iy. Alright, so think of the sign here. So this functional equation, if f of z is regular, and of course z is of the form x plus iy, and we have this functional equation here, then there are only three functions satisfying this property. So the first one is sine, the second one is the hyperbolic sine, and there is a third one, and I give this to a homework for you. There is a third function f of z satisfying this property. It's quite obvious if you take a close look, but play around with that. I hope you liked it. See you next time, and bye bye.